Before we start, you may be familiar with the term graph in the context of plotting values to a graph. This is actually different from graph theory graphs that we'll be talking about in this video. In a linked list, we store our data using nodes. So every single one of these nodes has a value, which can be Bob, for example, and we have a reference to the next node. Every single node has a value and a reference to the next node. But what if instead of one connection to a different node, we had a collection of references to different nodes? Graphs can be used to represent a wide variety of different ideas. So, for example, social media connections can be represented using graphs, or physical geographic distances, or network latency. So let's start with social media relationships. If we have 4 people, let's say Alice, Bob, Chris, and Dave. And these can represent accounts on a social media platform. Well, on a lot of social media platforms, you have ideas such as friends. So Alice sends a friend request to Bob, maybe Bob accepts it, and now Alice and Bob are friends. This connection between 2 nodes in a graph is known as an edge, or sometimes an arc. In this visualizer, I'm using just one data reference, that being a name, but in actuality, a node can store a lot of different attributes of data. So, for example, this node here contains the name Bob, but it could also contain an age, maybe an occupation or a favorite color or anything. If I was to include all of those, it would make the visualization a bit more difficult to see, but every node can hold more than just one piece of data. Friends in social media are a 2-way connection. If Bob and Chris are friends, then Chris and Bob are also friends. But what if we want to represent followers instead, where the connections are one way? Let's first remove these connections, and we can change a setting for the graph, which is whether it is directed or not. Now, a directed graph means that the direction of any connection, any arc or edge, is important. So, for example, maybe Dave follows Chris on a social media platform. Now, this doesn't mean that Chris can't also follow Dave. In this case, Chris and Dave both follow each other, but these 2 connections are separate. So whereas if it was like a friend system, Dave could remove Chris as a friend, and Chris would automatically have Dave removed as a friend. Whereas with followers, Chris can unfollow Dave, but Dave still follows Chris. You can have one-way connection between one person and another, and that other person in the original, but they can still be 2 separate connections. We've seen what it means for a graph to be directed or undirected, but what does it mean for a graph to be weighted or unweighted? A weighted graph is a graph where each of the connections has a value associated to it. So social media networks don't tend to do this, at least as far as I'm aware of. So let's switch from a social media example to a geographic example. So maybe we can represent the UK. We can have the United States of America. We can have maybe Poland. And we can have Spain. Now, the physical distance between the UK and the USA, I think, is approximately 7,000 kilometers. And so we can represent that distance on a weighted graph. The distance between the UK and Spain, I think, is about 1,500, and the distance from the UK to Poland is also about 1,500. And with this, you might be able to see where graphs can be quite useful for modeling problems. So we're going to break reality a little bit now and say that the distance between Spain and the US is about 50 kilometers. If we wanted to go from the US to Poland, and there's no direct flights, let's say, from US to Poland, we can't just go from the US straight to Poland. We need to go through a different country first. The most direct path here between US and Poland is through the UK. US, UK, and Poland. But if we instead want to look at the physical distance between two nodes in a graph, it might not be the same. So for example, the direct path between two locations might not be a straight arrow between them. There might be a very long winding road, for example, if you wanted to walk down it, and it might actually be quicker to go an indirect route and then get to your location first. So in this case, if I wanted to walk from Poland to the US, I would walk to the UK, I would then take the path to Spain and then walk from Spain to the US rather than going straight to the US. Now, I don't think walking between these four countries is a phenomenal idea, especially when it might involve crossing the Atlantic. But with different data, maybe between villages instead of countries, you can see why it might be a bit better to think about problems involving travel in terms of graphs rather than a list of distances. Maybe instead of physical distances, we want to represent time. So if we're currently in Spain and we want to fly back to the UK, maybe the next flight isn't until the following day. So let's say about 18 hours away, we'll get to the UK from Spain in about 20 hours. And let's make this directed as well. So about 20 hours. But maybe there's a flight from Spain to Poland in the next few hours, and we can get to Poland in, let's say, 6 hours. And then once we're in Poland, there might be a flight from Poland to the UK a few hours after that, which would take us 4 more hours. Now, most of the time when you're going to do this, these times, when you add them together, are going to be more than the direct path. But sometimes, like in the case where the next flight between Spain and the UK isn't until the following day, isn't for 20 hours, it might be quicker to go the indirect route. And graphs allow us to see, and they allow us to find some of the optimal paths. In fact, Dijkstra's algorithm is, which we will be looking at in a few videos, that's what Dijkstra's algorithm tries to do. It tries to find the shortest path between two nodes in a graph. A tree is a type of directed graph, as you can see here. Now, nodes in a tree can only have one node pointing to them, and this node is referred to as the parent. So for example, this node here with the default value of A has only one node pointing towards it, and that is this node here called root. Every node can have multiple nodes that it points to, but only one node can point to it. So the node that points to a given node is known as its parent, and the nodes that it points to are known as the children. A node that doesn't have any children, like these four at the bottom here, are known as leaf nodes. So in computer science, trees are usually drawn with the root at the top and the leaf nodes at the bottom. So you can tell computer scientists don't really leave the house very often. Trees are useful for representing data that is hierarchical in structure, for example, the file system on your computer. Binary trees are types of trees that, instead of having a collection of children, they have a left child and a right child. They can have 0 children if both of them have a value of null, 1 child if one of them is set to null, or 2 children where neither of them have a value of null. A binary tree cannot have, a node in a binary tree cannot have more than 2 children. And the 2 children that they do have are arranged left and right. Binary trees are especially important in searching in big data because it can allow you to ignore a large part of the data all at once. So for example, if we bring back Bob, Alice, and let's go Dave here and Chris here. And I'll just put a space in these so that it shows up as invisible. If we have data stored in this way, and we want to see if Alice is present in the data. Now, at the moment, we've only got 4 pieces of data, so it's not going to take very long to search one at a time. If we had them all stored in like an array, where they are 1, 2, 3, 4, then potentially we would have to search all 4 of them to see if a given value is present in the collection of data. If we store it in a tree, however, we can dramatically cut down the amount of checks that we have to do. If we want to see if Alice is present in the tree, we first compare the input value Alice to the root, and we can see that alphabetically, because it's in alphabetical order, Alice should be left of Bob. And what this means is that we can then look at this tree here. We can ignore this whole thing because all of the values to the right of Bob are going to have an alphabetical ordering of after B. Like if you sort it like you would in a dictionary, D comes after B, so it goes to the right. Chris will be inserted into the tree to the right of Bob and then to the left of Dave, and that's why Chris has been placed down here. This is quite a common idea, not just in trees, but also in binary search, as we'll see in a few videos' time. That's been graphs and trees. The next video will be about the bubble sort algorithm.